This is the question I was supposed to talk about. And I realized that I could actually say everything I wanted to say about this in one slide. And so rather than spend the entire talk talking about this, talk about something else instead. And the other thing is that I'm going to a lot of conferences this summer, and so it's likely that if you go to more than one conference, you'll see me at the other conference. And so I don't actually need to talk so much about my own research, because I'm sure I'll get it to you at one of these other conferences. So I thought about talking about something more broadly useful, which is making sense of everything we know about quenching and quiescence. Because it's really a little bit of a jumble when I go to a conference like this. There'll be talks about just very different kinds of galaxies. So elliptical galaxies, galaxies with HVN, quench galaxies, spiral galaxies. And it becomes really hard to untangle everything into a concrete formula for how galaxies form stars. We hear a lot of individual examples, but without so much organization and without so much ability to take what we learned about one type of galaxy, like elliptical galaxies, and translate that into what happens in other types of galaxies, like star-forming galaxies instead. So I thought I would try to make a way to sort out all these different things, and so we can make then inferences. Given one observational clue, relate that to another observational clue in a different type of galaxy. And so to do that, I'm just going to write down a sort of framework for galaxy formation, which is as simple as possible, but hopefully not any simpler. And that is, if I think about what galaxy formation is at its heart, we're just talking about how matter moves from one phase to another. And there's several different phases. I've condensed some of them, which you may argue are too condensed, but we have cosmic web, we have black mass, we have cold gas, we have H2 molecular clouds. I say particularly molecular clouds because diffused H2 I'm lumping them with cold gas because it can't so easily form stars. And then finally we have stars and black holes. And what we're really talking about is how does matter move from one of these phases to another and back again. And what are the kinds of links that we have? We have accretion and cooling, of course, from the cosmic web all the way down to stars and black holes. We have cold flows and mergers. So cold flows can get gas directly into, say, the cold gas reservoir. Mergers can bring in H2 clouds and stars and black holes. And in the opposite direction, we have feedback. So going from the stars, the galaxy, pushing material up and out. And the sort of flow chart is the flow chart of galaxies. And what we study with galaxy formation is what are the strengths of these links? What are the importance of these different paths of material flowing from the cosmic web into and out of galaxies? So using this diagram, I'll talk about now several important results over the past, say, year or so in galaxy formation about what sets the strength of these links, one, but also very interesting cases where if we break some of these links, say for satellite galaxies, where we break the accretion, or for galaxies with AGN feedback, or strong AGNs, where we say increase the feedback, what can we learn about the strength of these links and about galaxy formation from these examples where we've messed with this diagram in some way? Okay. So first key finding. So I'm sure that Ben gave an amazing talk on Monday, because I've heard it before, even though I wasn't there this time. But what I do is very similar to what he does, abundance matching across multiple redshifts. So if you match galaxies to dark matter halos at many redshifts, you can trace the buildup of galaxies over time and infer things like the star formation rate, which I've shown here, as a function of halo mass on the vertical axis and then time on the x-axis. And once you have something like a star formation rate in this way, you can then learn interesting things about galaxy formation. And what I've done here is divide the star formation rate in a halo by the average mass accretion rate of that halo as a function of halo mass and time. And so what you see here is a very beautiful picture where the star formation efficiency defined in this way as the star formation rate divided by the baryon accretion rate, really the incoming baryon conversion efficiency into stars. varies a lot with halo mass. And you see in the vertical direction 5 decades of variation, and not so much with time. And you see in the horizontal direction maybe 0.3 decades of variation, except for maybe this region here where you have no data to constrain it anyway. And this would suggest that halo mass is very important for setting the strength of these connections, whereas time, or redshift, is maybe less important. And the main effect of going back in time here is to scale up everything that's coming in on this left-hand side approximately equally. And so you almost have a linear system. Maybe that's just a coincidence, in fact probably is, but if you just double the amount of stuff coming in, then you end up doubling the star formation rate if you keep the halo mass fixed. And that's what this plot is showing you. But we can learn interesting things if we break some of these links. And so satellite galaxies are one of my favorite examples of this, because what you have in a satellite galaxy is you've broken all this accretion coming in. So you've obviously broken accretion coming in from the cosmic web, and not only just for satellites, but for galaxies well outside of the real radius of clusters. And so in this paper, which was published this year, I was showing that, for instance, at redshift 0, this black line, where incoming halos reach their peak mass before they fall into a cluster is actually more like twice the real radius of the cluster. And so tidal stripping begins at maybe twice the real radius, and so stripping is already happening while these things are falling in from 2 RVR to 1 RVR, and so the satellites are already starting to get stripped even before they become satellites. And so you've really just gotten rid of the accretion well before the satellite even becomes a satellite. But you also get rid of mergers, because even though the number density in real space of satellites gets higher as you get into a cluster, the velocity space dispersion also gets higher. And so what you see is, instead of things which can slowly fall into each other, they're just moving too quickly to be captured by each other's gravitational potentials. And so mergers also drop off quite rapidly once you get into a cluster environment. And so you've just axed out all the accretion. But the amazing thing about satellites is that there's no separate main sequence for satellite star formation. In fact, once a satellite becomes a satellite, it's as if you remember, I remember as a kid watching these Wile E. Coyote cartoons. And what happens is Wile E. Coyote is chasing Roadrunner, and oftentimes he'll chase Roadrunner off a cliff and continue running along the same direction until suddenly he looks down and realizes he's off the cliff and then falls. That's exactly what's happening with these satellites. They fall in and somehow keep on forming stars at the same rate, not completely oblivious to the fact that they've fallen into this giant hole, until finally, several years later, someone taps on the shoulder and says, "Hey, you're a satellite." And the satellite says, "Oh, I forgot, I'll stop forming stars now, sorry." And this is what this paper by Andrew Wetzel says basically, is that satellites spend quite a long time, 3 to 4 gigayears, forming stars on the same main sequence as centrals before suddenly quenching in a very short amount of time, a gigayear or less, and becoming off the main sequence.
Am I allowed to object slightly to that?
Sure.
So I broadly agree with that, but
Yeah.
if you do look at the color magnitude diagram of satellites in, for example, Frank's catalog, then they are, and you limit yourself just the face-on so that you're not being buggered by dust as usual.
Yeah.
Then you do end up seeing that there's rather more star-forming, but not enthusiastically star-forming galaxies. And so I think it's mostly true, but I do think that there is some some effect. It's not entirely the Wile E. Coyote model.
Yeah, so there's some effect, and there's some time also that things take to transition to the red sequence too. And so this picture isn't completely accurate, but a simplification.
Yeah. I agree, it's very close.
Yeah.
And shockingly close.
Yeah. And so in terms of what that says for physics of what's going on in these satellites, I would say that this link between hot gas and cold gas, this cooling, probably is not the main bottleneck for star formation in satellites. And that's because as the satellite falls in, the hot gas is getting stripped fairly easily. And even though it might have, say, 30% of its hot gas remaining, say after a couple of gig years, these long times are already 2 dynamical times, or I guess at redshift 0, this is basically 2 dynamical times. And if you go to even smaller galaxies, say 10 to the 8 solar masses, then these times keep on getting longer until finally you have 8 gig year delays before 10 to the 8 solar mass galaxies quench after they become satellites. And where does that number come from? That comes from the very large discrepancy between the quench fraction, which is say 10% at those galaxy masses, and the satellite fraction, which is 40% or more at those galaxy masses. And so you have to, I mean, there's no way out of it but to say that most of the satellites at that stellar mass are not quenched, and you have only a small fraction which have to wait for a very long time on average to be quenched. During which time, of course, all the hot gas is getting stripped away. And so if this were the bottleneck, hot gas going into cold gas, going to H2, going to stars, then you would see the star formation becoming quenched much sooner. But even though all the hot gas is going away, you're just left with a cold gas reservoir, these things are still forming stars. And then there's one other thing that you can learn from this is that whatever feedback is going on, not so much gas can be kicked out of this cold reservoir. Because if it were kicked out, what you would find is that if it either goes in the hot gas or goes in the host halo, it's not going to come back. Because the hot gas is getting stripped, and obviously if it goes in the host halo, it'll really be tightly stripped. And so it's not coming back. And so what that means is that whatever, say, supernova feedback is doing, the cold gas is not getting kicked out of the satellite, but it's still sticking around to some level before finally it runs out and then quenches. So why am I talking about satellite galaxies when actually most of this reading is devoted to more massive things? Well, if I draw the diagram like this for more massive galaxies, it doesn't look so different. And why doesn't it look so different? So I think we can all agree that the cold flows for massive galaxies aren't so in existence. I mean, because there's a virial shock, or a stable shock, either at the virial radius or further out, you don't have cold gas coming in. And if you ask about mergers, the mergers which come in, which could deposit cold gas, are actually tightly stripped well before they make it to the central galaxy. And so the way to see this is if you imagine you're in a 10 to the 14 to 10 to the 15 solar mass cluster, all the cold gas is going to be coming in halos, which are 10 to the 12 solar masses or less. So you have a factor of 1 to 100 in halo mass, and these tiny objects which are coming into this huge cluster are going to get tightly stripped and dispersed and mixed well before the material reaches the central galaxy. And this is really obvious for the stars, because if the stars actually made it to the central galaxy, you'd see a huge increase in central galaxy stellar masses between redshift 1 and redshift 0 within, say, a particular aperture. I know there are questions about how to do the fitting and so on. But within a particular aperture, we don't see a huge increase between redshift 1 and redshift 0 in terms of the stellar mass of massive galaxies. And that's really a clue that things are getting stripped well before. And so you don't have merges, you don't have cold flows, and so again, you've pretty much erased the side of the diagram, and you only have feedback and then some residual cooling going on. And so this goes to say that maybe massive galaxies and satellite galaxies aren't so different, but more of a spectrum. So the halo mass, of course, is determining the strength of this feedback, but it's not to say that there's a very different way of quenching satellite galaxies from quenching massive galaxies. And this, I think, underlies the success of this AIDS matching model, which you may have heard of by Andrew Heron and Doug Watson, which is similar to abundance matching, that stellar mass is matched to halo mass in decreasing rank order of size. But then star formation rate is set based on an age of the halo, which does not depend on whether the halo is a central or a satellite halo, but instead just depends on the mass accretion history, where satellites are just older purely because the recent mass accretion hasn't been so much. And this model is able to match, thank you, the quenched and star-forming clustering, as well as the quenched and star-forming separate weak lensing signals in Sloan extremely accurately for being such a simple model. Okay. So next I want to talk about gas around quench galaxies. And so for quench galaxies, we definitely know that accretion is going on, at least if they're a central galaxy, into the hot gas phase. Don't know about what's going on in the cold gas phase. We know that there's some dry mergers potentially as well, probably not H2, otherwise there'd be star formation, at least molecular clouds. And we know that there's feedback going on. The crazy thing is that this cold gas, which we know exists thanks to cost halos, is not cooling into H2. And so what's going on? Why isn't? Perhaps there's another channel. What's that?
How do you know?
That it's not cooling into H2 molecular clouds because otherwise the molecular clouds would then be forming stars.
Not necessarily.
I think it's pretty hard to prevent a molecular cloud from forming stars.
Well, molecular gas and molecular cloud, right?
Yes, and so that was why I was very careful to say at the beginning, I lumped diffuse molecular gas into the cold gas reservoir as opposed to the H2 reservoir. Yeah, so in other words, if there's a way to prevent this from cooling, and thanks to Kathy White and Rachel Somerville's paper, we have a very nice term, a parking lot, where this cold gas can just hang out. And why is it hanging out there and not cooling? I'm going to skip ahead.
I think Sandy Faber invented the parking lot term.
Okay, great.
It's very American to hang out in the
Eric?
parking lot.
What?
Sorry? It's very American to hang out in the parking lot.
I
Yeah.
know.
Yeah. So why is the gas just hanging out there? So it's interesting, if you look at galaxies with AGNs, where you'd expect that the feedback would be dramatically boosted. So, interesting thing. So we don't know necessarily if AGN activity is correlated or not with star forming activity, but one thing which we can say for sure is that the presence of an AGN doesn't automatically quench the star formation rate in galaxies. And so even though there's increased feedback going on with an AGN, we're not quenching things. And so that, to me, suggests, I mean, you could have many different models for this, and so this is mainly speculation, but to me that suggests is that gas which comes in cold flows from the cosmic web might be able to very easily channel into H2 and then the galaxy. But gas which is then recycled into the cold gas reservoir doesn't have such an easy time, and maybe the geometry is such that AGN feedback is more effective at keeping it there. So the main difference between quenched and star-forming galaxies is not the presence of an AGN, because you see AGN in both quenched and star-forming galaxies, but simply the presence of cold flows or the absence of cold flows. And the fact that the AGN is there is just keeping the re-infall from being very efficient at continuing to form stars. So that's, just to repeat that, an efficient way of cold flows coming in to form stars, but then the re-infall from ejected material is then not so efficiently coming back into the galaxy. And then the AGN is keeping that material there, even though that there's no star formation going on. Okay. And so then the last thing which I wanted to mention is merging galaxies. And if you come to Santa Cruz, I'll give you a much more in-depth talk about this. But for now, I'll have to show you this Patton paper. And with merging galaxies, you beef up all these different accretion rates. But the key with merging galaxies is that you don't increase all of these at the same time. So depending on the separation of the merging galaxies, first you increase the hot gas accretion rate, and then only when they get much closer do you increase the cold gas accretion rate, and then finally the molecular cloud accretion rate. And you can see a very clear signal as a function of distance. And the selection effects in this paper make it not the best way to show this, but the results that I get are very similar, is that you see almost no enhancement until you get down to 30 kiloparsecs for galaxies which are about the same size, and then you see a dramatic increase in the star formation rate, which is telling you perhaps that hot gas accretion is not so important for determining the star formation rate enhancement, but in fact you really need cold gas as well as H2 in order to increase the star formation rate in galaxies. Okay. So now I'll finish. Summary. If you think about the links in this way between these different reservoirs, I think it's a framework with which you can interpret many different observational results in terms of the same kind of theory of galaxy formation, and use different results to infer what must be going on in these different reservoirs. Satellite galaxies on this side may quench for much the same reason as their satellites, even though the physics why the accretion is being shut off is different. The quenching mechanism may actually not be so different between massive galaxies and satellite galaxies. Merging galaxies suggest that this hot gas path may not be so important, so quenching may just be a sign that no more cold flows are occurring, and it's just that the AGNs in galaxies are sustaining this or preventing easy reinfall from cold gas reservoirs. But of course you may have your own opinion. This is just my interpretation at the present time. Thank you.
Okay, Phil, can I ask you to set up? Okay, questions, Peter?
Yeah.
Okay.
We make this comparison between satellites and massive galaxies can still accrete from the hot phase, right?
Sure.
That's a big difference, because
Yeah.
at least in simulations we see the mass of the gas that we want to keep out from the galaxies coming from the hot phase. So at which extent are those two quenching mechanisms similar? Because satellites cannot accrete from the hot phase while massive galaxies can.
Yeah, so you can definitely accrete in the hot phase, but in massive galaxies, the cooling times for the hot phase are extremely long. And so you get very little cooling of that hot gas in the cold reservoir.
Not in the center of the
Not in the center of galaxies, that's completely true.
That's a big problem to keep them quiescent.
That's completely true. But you have less than m dot halo amount of stuff coming in. And in that sense, I mean, satellite galaxies, you also have cooling, some cooling from the hot phase, which is still around in satellite galaxies as well. But it's definitely not m dot halo of similar mass central galaxies. And so I agree it's an oversimplification, but it's an interesting parallel to draw between these two.
Question, Annabelle?
But your point was that the satellite had a whole lot of like cold gas reservoir. The expulsion of material from the galaxy should be minimal. That would mean that probably should be able to see a metallicity signal between a difference between satellites and the centrals, where you are still getting some kind of more substantial cooling from the hot, more pristine halo gathering. He just presented some results at the Robin Whitman Symposium, where he basically saying that he finds no instability and point contents of satellites and centrals. So can you comment on that in light of what you described?
I'd have to think about that result more. So that's interesting. And I don't know immediately how quickly the metallicity would change. Because the continued star formation rates for satellites at the present day, I mean, the specific star formation rates are not so great, and so I don't know if the metallicity would be expected to change rapidly or not.
Anna
but that's
Pasquale has
interesting.
written 2 papers comparing centrals and satellites at the same stellar mass, and she did find significant differences both in the gas phase metallicity and the stellar metallicity between centrals and satellites matched at stellar mass. So
Okay, so there's some tension.
There's some tension there.
Interesting. Yeah.
Because I was basically wondering, you categorically say that you must shut off the accretion onto the satellites, basically. I'm not entirely sure why that necessarily must be the case. I mean, if you had a cycle of gas into the satellites and out of them again at some rate, then you would get similar effects. And that's awesome.
So one quick question, Arjen?
So what in your mind first quenches a 10 to 11 solar mass galaxy, say redshift 2, what stops that cold flow in the first place?
I think when the halo mass, I guess I forgot to even say anything about massive galaxies, so maybe I should say that now. Since Greg asked me all the way here because of that. So I think that's just because the host halo gets so big that you no longer have cold flows coming in. Eventually the cold gas gets exhausted, and then you just have no more gas.
That's not,
You don't think so?
that's not what's happening.
In these massive galaxies of redshift 2?
Well, I mean, but I see no reason to have a tooth fairy at redshift 2 and a different tooth fairy at redshift 1.3.
I don't think there's a different tooth fairy going on here. I think just when the
In
halo mass
that case,
gets above...
I'm reasonably confident that that tooth fairy alone is not all that's happening.
So I think we can show that the star formation efficiency, that is the star formation divided by the incoming mass, no matter what redshift, once the halo gets above 10 to the 12, it becomes much less efficient.
I understand that's how you model it, but you don't
Yeah.
necessarily
Why?
have, I mean, you have a halo mass, but you don't necessarily have all the other bits and pieces,
That's true.
right?
Okay,
That's
let's
true. But
move
we
it
can
on
we
to
can
the discussion because we need to move on.